Okay, so here we go. This is our second video for vector. This is actually entitled Vector Resolution, with of course the hidden seed. And what we can understand is that what do we mean by vector resolution? Well, the point to remember here is that vectors can be resolved to give us what is called the resultant vector. Another word for resultant in physics is net. It's a combination of all the different forces or resultant of vectors, and the directions, and to be able to solve for a value that would indicate all of their directions into play, which I will show you in a little bit. Now, what do you mean by this? We already established in our animated video, this vectors with vector animation with Frank, that what basically a vector entails and what is the difference between a scalar and a vector. So you take a look at it. And what we'll start off with is there are two ways so we can classify vectors, pretty much. A vector can either be parallel, or vectors can either be parallel, I should say, or non-parallel. Let's take a look at parallel to begin with. Okay, so we want to go through, first of all, what are parallel vectors? Parallel vectors really and truly act along the same plane. What I mean by same plane, it can be the x plane along the x-axis. It can be along the y-axis vertically. It can be diagonally along the xy plane, etc. So what we have to pay attention to is our directions of such vectors. So let's say we have two vectors, for example, one 5 newtons and of course the other, let's say 8 newtons, acting in the same direction along the same plane, hence the reason why we are calling them parallel vectors. Well, we treat them like two addition signs as we would in normal mathematics. We can always say going right is positive. Of course, that's not always the case. We can choose the directions. So when it's time basically to add them, we will add them as 5 plus 8 to give us 13 newtons. Drawn to scale, it will be one horizontal line with an arrow pointing in the same direction that we are starting with because it's positive 13 newtons. This would give us, if we are adding, of course, these two vectors. So this is addition of the parallel of all parallel vectors. Another example is, let's say, if we have two vectors, same 5 and let's say 8 newtons, but they are in opposite directions. I'm using a horizontal axis just to help us out. We can set, as we said, positive is to the right direction. We can take our negative direction as left. And what we do, we add them if you need to add them physically, as you would in mathematics. When you add two numbers, the number takes a sign of the larger number. When you add two numbers, one negative and of course with different signs, one negative and one positive, the answer will take the sign, a plus or a minus is a minus. So the answer takes the sign of a larger number. So we will get minus 3 newtons. What does that mean for us in vectors? We established the fact that going right, and you could take a number line to always help you, is positive, left, it's negative. So our answer here will be a 3 Newton force going left. Of course, we can just put 3 newtons and put your arrow to indicate this. These are examples of what we call resultant vectors. So our 13 Newton force is our resultant vector. And our 3 Newton force going left is also a resultant vector. So we have just resolved those forces. Or we say we have done resolution of vectors. So what we're going to look at here is a simple concept of what this vector, or this parallelogram more specifically, of vector for parallelogram of forces in this case really means to us. So opposite forces are going to be the same. Opposite lengths, that is, are going to be the same length. So this 3 Newton force is also going to be, this dotted line is also going to be a 3 Newton force. The 2 Newton force opposite to that, same direction, it's also going to be a 2 Newton force. A lot of times people forget your directions and you can't. So what does this mean? How do we get from this? We can complete a parallelogram, no problem. How do we get from this, therefore, the resultant? Well, we want to create, therefore, your resultant. An important thing to remember at all times with resultant is that it will always act in the opposite direction to the general flow of arrows. As you notice, there's no one flow of the arrows, so we need to get our resultant. I've started with here, this is our starting. Well, this is where the object possibly is. If it can move upwards, followed by across 3 newtons, then this would be the path in which the object could possibly move. That will give us our resultant, practically speaking. Or I can take the base triangle where I'm moving 3 newtons across to the right, followed by 2 newtons upwards. It will still arrive at the same end point. Alright, this is our end point for our parallelogram. This is our starting point where the object will have been placed with such a situation. Now this is therefore our resultant vector. I'm going to call it FR. Our resultant vector, therefore, an important thing to remember is that it is the opposite, it acts in the opposite direction to the general sense. General sense, really in physics, general sense, a sense means the direction of our arrows. So in the general sense of our direction of force, or general sense of our forces that we have on our quest in our diagram, parallelogram. So this being a resultant is all well and fine, and of course being a right angle triangle, it's a parallelogram. So we have just created 2 right angle triangles. Let me break this down. So how can I actually say I'm creating 2 right angle triangles? Well, this is one. Sorry, it's quite bent. So this is the other, right? So we have 2. This is your resultant force. You got some here. This is also a resultant force. 90 degrees, of course, our 90 degrees. This is a 3 Newton force. Each time you write a force, you put an arrow next to it to indicate direction. That's what really and truly a vector really means. So this is 3 Newtons across here, 2 Newtons here. We have just created 2 identical triangles, right angle triangles that we can now use. Now they're not always going to be right angle triangles, as we will see. But an important thing to remember right here is that yes, we can use, of course, taking any one of these right angle triangles. And I'm going to take the base one, for example. So I'm going to take this one. Our base right angle triangle means we can now find our resultant. And yes, forgot my arrow. While we include our arrows, 2 Newtons going across, 3 Newtons, I'm going upwards, sorry, and 3 Newtons going across, our resultant is actually found by very famous Pythagoras' theorem. Pythagoras' theorem is used to find any missing length in a right angle triangle. So what our Pythagoras' theorem is FR squared is equal to 2 squared plus 3 squared. Of course, this would be 4 plus 9, which is 13. And FR, our resultant, is the square root of that 13, which of course in this case, what will it be? Can I leave it as root of 13? Of course you can, but I'm going to just take a note of it. Alright, so our square root of 13, we got 3.6. So just want to make sure. Those 3.6 therefore newtons, but that is not our final answer. When we are asked to find the resultant vector, we always find an angle with respect to any one of our forces given. So why is this so important? Because a resultant vector can go in that diagonal. We can say, yes, of course, well, if a ship, for example, is being towed, we say, okay, fine, it's good, the resultant vector goes in a diagonal. It's going northeast. But northeast without an angle doesn't give a correct indication of where the ship is going to arrive, if this was in fact a ship being towed by 2 tugboats, for example. So what we need to do is find an angle. And in that instance, you can call any of the angles. I'm calling it theta. I'm going to find the angle between FR and, of course, our horizontal force. You can literally find any angle, but you need to identify it. So how do we find this angle? Of course, this is being theta, right? Of course, from our triangle, this is theta as well. I'm going up here to do that to make sure we are okay with it. So how do we find that angle? I'm going to use tan. Why am I going to use tan? At this point, you can use sine, cos, or tan. But keep in mind that we are using tan simply because in case you make a little error in finding your resultant, we were given these 2 values for tan, our opposite, and our adjacent sides in our question. So tan is opposite by definition over the adjacent, side. So our opposite side is 2, adjacent is 2 over 3. but we will end up with this 2/3. And what we say is a theta is tan inverse of this 2/3. What we will end up with is theta being 33.7 degrees or 34 degrees. So what is our resultant vector? It is Fr, which is 3.6 newtons at an angle theta to the horizontal force. That's our first example. Now, I just want to indicate something very specific. We mentioned just now, and of course, a moment ago, we had mentioned that our resultant will act in the opposite direction. My diagram is terribly drawn. A resultant ended up in your opposite direction. So we ended up with, or we started with a 2 Newton force, a 3 Newton force, and different values, of course, given. And our resultant ended up in our opposite direction to the general sense, as we said, of these arrows. What is so important about this? Because if our resultant acts in the opposite direction, what is acting in the same direction of these two forces? So as you notice, you might say, oh, well, it might be tempting, therefore, to draw a triangle like this. 3 newtons across, you have your 2 newtons upwards. And by completing the parallelogram, you might end up with a triangle that looks like that. And of course, it might be tempting to say, okay, so it's going in the same, everything, all forces going in the same direction. That's not the case. That is no longer called the resultant. This force is actually keeping these two other forces in equilibrium, and it's called the equilibrant force. So the equilibrant, it follows, is that force that sorry, I'm going to take a note of it. It is required to stop a body from moving, meaning it's going to keep it in what is called static equilibrium. And a point to note here is that the equilibrant and your resultant will always be in opposite directions. It's along the same straight line, the same plane, but it acts in opposite direction. All right, so just a point that I wanted you to know before we go on. There are other types or other examples with regard to our parallelogram of vectors, but let's take it up a notch. Let us solve a question using we'll find the resultant using our parallelogram of forces, but not using forces that are placed at right angles to each other. Okay, so here we have another example, our example number 2 for non-parallel vectors. And for example number 2, let's consider two forces acting at, let's say, 30 degrees away from each other. Your first force is 3 newtons at a diagonal, and the other force is your horizontal force of 4 newtons. They want us to find, in a question like this, our resultant force. So it's either written as resultant force, net force, etc. I can just put it as FR. Now, how do we do something like this? Are we actually, in fact, going to use a parallelogram of forces? Yes, we are. So we start off by saying this is our solution that begins here. I'm going to complete my parallelogram. Please forgive my lines of 4 Newton force, 3 Newton force. This is our starting point. This could again be considered a boat that is being towed by two tugboats. Of course, the force is not being exactly real. So this is 30 for now. So I'm going to complete this parallelogram so I can show you. I'm going to complete. This is not drawn to scale clearly, okay? So this is 4 newtons again, 3 newtons acting in the same direction, and you stop to check to make sure that your two opposite forces are not just the same, approximately the same length, if it's a sketch, but they're also facing the same directions. So once again, another thing to note, we can also do this drawn to scale, but I will get to that in a little bit. Our resultant is taken from here to our endpoint. This is therefore our resultant force. But keep in mind that we were given 30 degrees as that angle. This is 30 degrees. That is not necessarily the angle. Our resultant is not necessarily, and of course is not, passing through at 15 degrees. We're going to cut this angle at 15 degrees simply because these two sides are not the same. These two forces, I should say more specifically, are not the same. So we need to find out what angle we can use. Again, I'm going to take my base. Okay, in this case, I'm going to take this top triangle. And I'm just going to isolate that. Why? Because I want you all to see what our resultant force is and that relationship. We are given this 3 Newton force, we have a 4 Newton force. We need an angle to find this third force, our resultant. Always double check to make sure that your arrows are, your resultant is in the opposite direction to your general sense or your general flow of your arrows in your question. So let's analyze. What is that force that we are missing? Well, this is really angles right here. I'll do it in blue so you can see it. If I continue this straight line, this angle is 30 degrees as well. That's all. Alternate angles. This angle, therefore, is what we could actually use to help us out. And that's 180 minus 30, which is, of course, 150 degrees. If we add them both, we get the angle. If you look at a protractor, for example, of a straight line, which is 180 degrees. This is our angle that we are going to be using. Why? Because if this is 150 down here, this is also in a parallelogram, the opposite angles. That's also 150, it's the same. So this is 150 degrees. What do we use to find this resultant vector? Well, we use a simple mathematical concept called the cosine rule. So the cosine rule basically mimics Pythagoras' theorem, but it involves an angle. So how do we get the cosine rule? I'm going to say f. I'm going to just call it f now. F squared is equal to the sum. Notice how it starts off the same way, right? Minus, I'm going to use the brackets now, 2 by, sorry, not 2, 3 by 4 minus, oh, I made a little error, sorry. This is actually not 3 by 4, it's supposed to be 2 times. So just those of you who to remember, just to remember something, I'll rewrite Pythagoras' theorem so you can see it in a little bit. But what I want you to note is that if yes, it is 2 times 3 by 4 by cos of the angle, which is of course between 3 and 4, these two forces. That is cos of 150 degrees. There's a reason why I put this in brackets. You're going to realize that just now. Now, if you need to remember what Pythagoras is, the cosine rule is, it's given normally if you use a as your longest side. A squared is equal to b squared plus c squared minus 2 times BC, these two forces right here, cos of the angle between those two C forces, B and C. And of course, it's also opposite to our side that we're trying to find, which is opposite to the angle E. This is how we get, this is our cosine rule, as we said. Alright, so it's a mathematical concept. You can do it another way to prove it in another video if you need to see it. I'm going to substitute. I'm going to actually work it out, sorry. And in doing that, what you're going to realize is that yes, we are using the cosine rule, but our final value is going to be f squared. If we find the resultant, of course, of that, the square root of that, you're going to get a value. So a point to note of this is how do we find the sine of the angle? Well, to find theta, we end up using, or we're going to use something called the sine rule. Now, is another mathematical concept, and of course, is another rule that we use in trigonometry. So, in what is the sine rule? It is the ratio of one side to its opposite angle, the sine of the opposite angle. So, what is the side and opposite angle corresponding with? We want to find theta. So, we should include theta as our angle. And of course, opposite to that value, theta is where these two sides, well, they subtend, first of all, to form theta, but opposite to angle theta, bottom line is that it's 3 newtons, right? So 3 newtons corresponds to theta. And we already have, we are not given this third, the other angle opposite to 4 newtons, so we are not going to include 4 newtons as our part of our question. What we can include, however, is what we just found, which is our resultant, and I'm going to write it in 6.77 newtons. Now, what corresponds to 6.77, what angle that is, corresponds to 6.77 newtons, 150 degrees. So our sine rule is a ratio of one side, in this case force, to the opposite angle. So I'm going to put 3 newtons over the ratio, the sine ratio of its opposite angle, or sine of the opposite angle to 3 newtons. It's equal to FR, which is 6.77 over sine of its opposite angle, which is 150 degrees. Of course, when we cross multiply, we will get 6.77 by sine theta multiplied by sine theta is 3 sine 150 degrees. Now, that being said, we will end up with that sine theta is of course 0.222. So theta is of course, so we said, is sine inverse of 0.222. So theta ends up being 12.8 degrees. You are also allowed to put it as 13 degrees because of course the error in reading an instrument for in terms of protractor is plus or minus 1 degree. But I'm leaving it as is for now. Three significant figures because my force was also given to three significant figures. So what is our final answer? Our final answer is that I'm just going to put a little note here to highlight it. All right. Our final answer here basically is, oh, that's not right. Right. So our final answer basically here, okay, let me just write it. Would be for FR, which is 6.77 newtons, at an angle theta, of course, we said to the horizontal. All right, so it's 12.8. That is our theta value. Our value of 12.8, therefore, and of course, noting that it is 12.8 as our value. 12.8 is going to be that angle between your our 4 Newton force and our resultant. So this is how we relate our question. Okay, any questions you'll have, please feel free to ask once again. And I will do a few more questions based on this. Oh, point to note with this is that you can actually find the resultant vector by drawing a diagram to scale. So you use a protractor instead of having to work them out using the cosine rule and the sine rule. If you draw this diagram, original diagram to scale, and of course hence your parallelogram of vectors, you just have to measure your resultant force. Now, this works for smaller values for forces, but if they're very large, for example, 250, 200, etc., if this was a 300 Newton force, for example, we would need to scale the diagram down, as if we would if we had to draw a graph. So we could use maybe 1 Newton, 1 centimeter with 100 Newtons, for example, just to give you an idea of what it may look like. If you need me to do any of those, please let me know, and I will do a few more examples with finding the resultant when it's not actually just two non-parallel vectors. Thank you.